If you've ever wondered how your air conditioning or heating system actually moves water through pipes to keep your building comfortable, you're about to find out. Today we're breaking down one of the most important but often overlooked components in HVAC systems, the pump. Whether you're a technician, a building manager, or just someone curious about how these systems work, understanding pumps will give you serious insight into climate control. If you want to stay updated on HVAC knowledge and practical maintenance tips, go ahead and subscribe to the channel. So what exactly is an HVAC pump? At its core, a pump is a mechanical device that moves liquid, usually water or a water glycol mixture, from one point to another. In HVAC systems, pumps circulate water through pipes to absorb or reject heat. Instead of using the refrigerant itself to travel through large sections of a building, we use water as the medium. This is actually a much smarter approach than you might think. Why do we use pumps and water pipes instead of running refrigerant lines everywhere? Well, refrigerant is expensive, hazardous, and requires specialized handling. It also needs to be in a closed loop with very specific pressure conditions. Water, on the other hand, is cheap, safe, and easy to work with. You can run water pipes through walls, ceilings, and under floors without the same regulatory concerns. Water can move heat over longer distances more efficiently than refrigerant alone. Plus, if you ever need repairs, dealing with water is far simpler than recovering and storing refrigerant. So pumps became the standard solution for central HVAC systems. Now let's dive into how centrifugal pumps actually work, because they're the most common type in HVAC. Imagine you have a spinning wheel inside a circular chamber. That wheel is called an impeller. When the motor spins the impeller really fast, something interesting happens. Water enters near the center, right at the eye of the impeller. As the impeller spins, it flings the water outward using centrifugal force, kind of like a merry-go-round, throwing riders toward the edge. This spinning action creates a low-pressure zone in the center and a high-pressure zone at the outer edge. As water moves from the center toward the outer edge of the impeller, it gains velocity and pressure. The curved shape of the impeller blades guides the water in a spiral path, building speed as it goes. Once that water reaches the outer edge, it gets forced into a specially shaped chamber called the volute. The volute is designed to slow the water down gradually, converting all that velocity back into pressure. This is how the pump creates the pressure needed to push water through miles of piping in a building. Let's talk specifically about pump impellers, because they're really the heart of the whole operation. The impeller is precision engineered to move water efficiently. Most HVAC pump impellers are made of cast iron, bronze, or stainless steel to resist corrosion from water and mineral buildup. The blades are curved and angled in a specific way. If you were to look at an impeller from the side, you'd see a beautiful spiral pattern. Each blade is positioned to catch water and accelerate it outward in a smooth, continuous motion. The size and shape of the impeller determines how much water the pump can move and how much pressure it creates. A larger impeller with more aggressive blade angles will move more water faster, but also creates higher pressure. Smaller impellers are gentler and use less energy, but they move less water. Engineers choose the right impeller size based on the building's heating and cooling demands. The impeller also needs clearance inside the pump housing. Too much clearance, and water leaks back toward the intake. Too little clearance, and friction builds up, causing wear and heat. Now here's where it gets interesting. Not all water in an HVAC system is the same. Buildings use two different types of pumps for two different purposes. First, there are chilled water pumps. These move water that's been cooled by a chiller unit. This cold water circulates through cooling coils and air handlers and fan coils throughout the building. When warm air from the building passes over these cold coils, heat transfers from the air to the water. The chilled water absorbs that heat and returns to the chiller to be cooled again. Chilled water pumps need to be reliable and efficient because they run almost constantly during summer months. Then you have condenser water pumps. These do the opposite job. They move water that's been heated by the refrigerant in the chiller. This hot water gets pumped to a cooling tower where it's exposed to air and ambient conditions. As the water trickles down through the cooling tower, air blows up through it, evaporating some of the water and cooling the rest. This cooled water then returns to the chiller to absorb more heat from the refrigerant cycle. Condenser water pumps often handle harder work because condenser water is hotter and more prone to scaling and corrosion. Both types of pumps look similar and work on the same centrifugal principles, but they're selected and sized for their specific application. Chilled water pumps are usually sized for moderate flow rates and lower pressure requirements. Condenser water pumps are often sized for higher flow rates because cooling towers need more water volume to cool effectively. Here's a concept that confuses a lot of people: primary versus secondary pumping. In large buildings, you'll often see two separate pump circuits instead of one. The primary pump is connected directly to the chiller or heat source. It runs constantly to create a minimum flow rate through the chiller itself. This protects the chiller from damage. Chillers need a certain minimum water velocity flowing through them at all times. If flow drops too low, temperature distribution inside the chiller becomes uneven, which can damage the unit. The secondary pump is what actually serves the building. It pumps water from the distribution loop through the air handlers and cooling coils where people actually need the cooling. Secondary pumps can be turned on and off or modulated based on demand. This is much more efficient than running one huge pump all the time. The primary pump keeps the chiller happy, and the secondary pump serves the loads. They're connected through a common return line, so they work together as a system. This setup gives you flexibility. You can have multiple secondary pump circuits for different zones or different parts of the building. You can stage secondary pumps on and off as cooling demand changes. The primary pump just keeps doing its steady job. This is how modern buildings achieve efficiency while keeping equipment safe and operational. Like this video if you've learned something useful so far, because understanding primary and secondary pumping is crucial for anyone working with HVAC systems. Now let's talk about what goes wrong with pumps. One of the most common problems is cavitation. Cavitation happens when pressure drops so low that water actually turns into vapor bubbles inside the pump. When those bubbles collapse, they create shock waves that pit and damage the impeller and pump housing. You'll hear a loud rattling or grinding noise if cavitation is happening. It usually occurs when the suction side of the pump isn't getting enough pressure, maybe because the water level in the tank is low or the intake filter is clogged. Another frequent issue is bearing wear. Pump bearings support the spinning shaft and handle tremendous loads. Over time, especially if water quality is poor or the pump cavitates, bearings wear down. You'll notice increased vibration and noise. Eventually, bearings can seize completely, and the pump stops moving water. Bearing replacement is one of the most common pump repairs. Sealing problems are also very common. Pumps have seals around the shaft where the spinning part goes through the housing. These mechanical seals prevent water from leaking along the shaft. If seals fail, water starts dripping out of the pump. Not only do you lose water, but air can enter the system, which causes all kinds of problems downstream. Seals can fail due to wear, misalignment, cavitation, or contamination from particles in the water.